I'll start in 2 minutes. Not my student. Time to do something. For example, to speak, to continue our theme with symmetrical components or modal transformation. Now, where we are, what I'm talking about. See, previous I draw this nice schematics. It's a direct negative and zero sequence. Very fine. We can create something like this. And it will be for us a model for line to ground fault at this point with the transient resistance of RF. Very nice. But what inside here? What's in this box? I draw nice equivalence, but what's in? And this one. All this with one particular purpose, to analyze operations of ground fault protection. There is no reasonable way to analyze ground fault protection without deep analysis of this part. So, what's in the reality of modal transformation? I need to create a model in terms of modal transformation. I need to create three schematics for each of the sequence. So instead of one three-phase network, I will get three single-phase network. If there is no some special needs, I will operate with phase A. It's easy, it reduces calculus work. But I will need three separate schematics for direct sequence, for negative sequence, and for zero sequence. At a first, let's say, in a simple approach, in a common approach, they will correspond to phase A. So, I can have multiple objects. For example, there could be a system. If, say, for example, here I have 20 kilovolt distribution network, 110 kilovolt supply network, and my fault is here. It can be not ground, but let's say it will be BC fault, line to line. Distribution networks here operate in isolated neutral mode. All 110 kilovolts part should be I can dispense it or represent as a system. So system in direct sequence, it will be AMF divided by square root of 3. This is direct sequence neutral and ground. There may be a system. Usually it's only reactive part is accounted, but see, it can be system resistance. Your neighbor can supply you, or you can have it in the form of fault power. It's a power what will be supplied to the point of fault in case of three-phase fault. For negative sequence, will be the same system impedance. For zero sequence, approximately X system, but take care. If you have a data, fault calculus date, there may be a difference. When the difference can be one possibility. When people from this network operator, when they calculated this equivalent resistance, they may took into account connecting line. If this line are long enough, you will see increase in zero sequence. So if you have paper from network operator, check what they calculated. Maybe they will give you a bit higher resistance. Next one. There should be generators. Generator. It should be quadruple AMF and longitude reactance. In direct sequence. Be careful. This value changes in time. For any rotating machine, at the first moment of transient, if you close enough to machine, there will be you should use so-called transient AMF. For any rotating generator in the first moments of the fault, transient AMF should be used. It takes into account transients in magnetic system of generator. It's approximately 5 to 7% higher. Also, it came from manufacturers. Transient reactance. It's smaller than stable regime. If this data, if fault is far enough and machine voltage changes a little. If you have fault in some way in proximity of your machine, take a look into machine data. Manufacturers supply with transient EMF and transient resistance. That's not all. That's not all. There is one how to say, maybe disadvantage or possible problem with synchronous machines. Simple synchronous machine without some special means do not have or have very small asynchronous torque. This means that inside pole division rotor can oscillate. It has a very negative impact, especially on hydroplanes. When load is low, mechanical load is low, supplied active power low, generator can oscillate. It will be in horizontal. It will oscillate like this inside pole division. This can cause first very fast degradation of machine bearing. Lower bearing on modern machine, it's rubber or some composite greased, how to say, with water. It's water immersed bearing. This bearing takes all the weight of rotor with its turbine wheel. 500, 700 tons. Backwards rotation extremely means extremely fast degradation of this bearing. They are not, how to say, they are not designed, they are not intended to two-way rotation. It's one thing. Second, turbine, this work wheel with propellers, can suffer from the so-called cavitation process. What's mean cavitation? When the vein goes through the water flow, on its, not leading, but on its tailing end, low pressure area being created. So it's an area of low pressure. And its area of low pressure, water boils and becomes saturated with small bubbles of steam. Then, when they collapse and hydraulic heat, when these bubbles collapse, water by inertia heats the backward, back surface of the vein, causing metal erosion. Long walked turbine wheels has holes, make holes like this, eaten by cavitation. Backward movement causes cavitation damage on the leading edge. It's hardly repairable, it's a bad thing. And then on the tailing edge. This can cause crack, how to say it, these fasters, crack formation and vein breakout. So it will be heavy damage to the machine. That's why this oscillation should be suspended, or how to say, dumped. To do so, special technique is used. On large hydro generators, front surfaces of the poles are made with special how to say, grooves, special cut-ins for the short circuit winding. And kind of very massive copper rings are placed here. When machine rotates synchronously, there is no speed difference between stator magnetic field and the rotor. That means what current in these rings is zero. When oscillations begin on very early stage, maybe because of irregularities in water flow, current will be induced. There will be no that appears as synchronous effect. Current will be induced in this ring, and magnetic field of this ring will, how to say, break the rotor. It will act as a damper. When transient happens, near transient, first to act will be a magnetic flux inside these rings. So for hydro plants, super transient EMF and reactance should be accounted. Actually, in time, fault current looks like this. First stage, super transient, then transient, over is a steady G. Why it goes up? Because voltage control system do not understand what it's a fault, and it will rise. So this rise is caused by excitement system rising the exciting current. So it will be slow rise. If you do not disconnect, if you do not timely clear the fault. Next, so this is for direct sequence. Super transient, transient, steady. Super transient, transient, steady. In case of negative sequence, what we will get with our machine? Problems we will get, problems. Much depends on presence of damping winding. For the magnetic field of negative sequence, our machine rotates in counter direction with double speed. So if in direct sequence machine has a speed omega, in the negative sequence to the field 1 omega, again omega, delta equals double omega. This is a double slide, meaning what in all closed counters in rotor will be induced current. For hydro generators, for generators with this short circuit winding in the surface of poles, so for machines with damping winding, this poses little danger because negative sequence current will close in this short circuit rings. For steam generators, for generators without damping winding, negative sequence poses a very high degree of danger. Because rotor shaft will overheat. Some machines had metal winded bondage with the excitement, holding excitement winding. It will cause overheat of the power fixtures. It's dangerous. It causes rotor overheat. Turbo generator, steam generator, should be immediately disconnected from network if negative sequence is above 10% of direct. Put this number. As reactance for negative sequence, something about approximate transient reactance should be accounted, but again, take a time to look into manufacturer's data. Usually, manufacturers do supply you with this number. Very approximately, I can tell you. More approximately under 100 megawatts over the super transient EMF will be plus 8%. For machines from 100 to 500 megawatts, approximately plus 14%. For synchronous compensators, plus 20%. Over this super transient reactance, for small turbines, something like 12-15% in relative. For large turbo, 12%. And for synchronous compensator, something about 20%. It's superimposed. Super transient, sorry. If you would like to know more, this book is available. Check 2.4 article. Now what about zero sequence? What about zero sequence? There is two, let's say, group of machines. 99, okay, not 9. I don't know exact numbers, but I don't know exact numbers, but if we speak on any megawatt and upper class machine, we will see one important moment common. These machines are usually operated in an isolated network mode. What I mean? Typical connection for the synchronous machine starting from megawatt and up will be, I'll draw, it's a machine that maybe, okay, I will save space. So it's this switch, not always. For large machine don't have this switch. Transformer delta start 110 and up kilovolt network. Here this switch is always present, but this one not always. For problem high fault current makes this switch so expensive and so unreliable. 100 and up megawatt machines usually don't have it. They operate as a one unit with transformer, or can be designed one transformer for two generators. It's such kind of design also present. And what? Neutral is connected to the ground via voltage transformer. Oh, I will schematically voltage relay. This is neutral displacement relay. It's signals isolation fault of the stator. So generator operates in the isolated neutral network. It's always, for large machine, it's always like this. Because this schematics is safe and it saves costs. For such schematics, this zero sequence resistance of this scheme is determined by triple Z mu of this transformer. Consumption of the relay is neglectable, and we will see in reality. If you want, our relay, something like this, multiplied by 3. It's a very high resistance. So, for zero sequence, there will be no zero sequence. For zero sequence, we will see infinite resistance. It's for large machines. For small machines connected directly to the network. In case of direct connection to the network, it's usually a very small hydropower plant. and something like mobile diesel generator, or small scale, some kind of small scale diesel powered generators. For such generators, we are in problem. For all the problem is that zero sequence flux can flow as a direct sequence flux. Zero sequence flux, because sum of phase fluxes will be triple, not zero, it goes from the windings, then goes outside along with the machine rotor and closes around SA. Kind of nomad flux. It's a flux in dissipation. Flux flows through bearings, through shaft and side. For old designs where cast iron, there's bearing, we call them bearing shields. This bearing support or this side covers of machine were made of cast iron with good magnetic conductivity. Meaning what machine will have good magnetic conductivity for zero sequence and appear with some notable reactive resistance. For modern machines, we can expect aluminium castings and aluminium shroud around the main main starter magnetic system is made of steel shields, and it's put in shroud. Old machine had cast iron shrouds. Again, with good magnetic conductivity. So we can expect some inductive resistance from such kind of machine. Modern have aluminium shroud and aluminium bearing supports. Bad magnetic conductivity. Bad magnetic conductivity means very low inductance, very low resistance. So this machine possibly will have some small, much smaller resistance in the zero sequence network. What means small resistance? See, you need to understand. Flux of zero sequence is steady. Direct sequence rotates forward, negative sequence rotates backward, but zero sequence do not rotate at all. It's pulse on a place. Magnetic field of zero sequence is on do not rotate. If field do not rotate, but machine rotor is rotates with synchronous speed, you will have slight 1 omega or speed difference between speed of the rotation of magnetic field and field of the zero sequence. This means what? You will have induced current in your rotor. This means overheat of rotor. Shaft will suffer. All kind of fixtures for poles, bearings will suffer. They are not intended to be a magnetic part of magnetic circuit. Asymmetrical load are not welcomed by diesel machines, believe me. It causes rotor overheat and damage. But what I'm willing to tell, I say, when we deal with zero sequence on such small machines directly connected to the network, we will not have good precise numbers. Actually, sometimes two identical design, sequence serial numbers, one design, two machines, difference 30%, something like this. So if you don't have a test data, measure. And better to measure after assembly, because for this dissipated magnetic flux, all kind of cover, shroud, supports, cooling, even cooling pipeline may change distribution of magnetic field and resulting resistance. No way to get a good data. What's next? What's next? Asynchronous machines, motors. For asynchronous machines, you will get, if you open a handbook, take a manufacturer handbook and you will find transient reactance, normal active resistance, general schematics like this. This is primary winding, magnetizing circuit, secondary, this is resistance of secondary winding copper, and this active resistance, for machine load. Here, slide is omega machine and it's omega net divided by omega net. If machine rotates synchronously with synchronous speed, it will be 0. If machine has a speed of 0, it stands still, it will be 1. Slide related. For direct sequence, actually, if you need very precise date for the transient, take into account your asynchronous machine in the first seconds of milliseconds of the transient will supply you your network with energy. It's for short time you can use AMF approximately 0.9 and transient reactance something like something about 0.3. It's for short. For quite stable modes, you can use simple transient reactance. That's for direct sequence. In case of negative sequence, and asynchronous machines don't like that, you will have not S, but 2 minus S in case of negative sequence. And machine, actually, for some machines, this data of negative sequence reactants are available, but not for all. If you got it, good. No, just take transient reactants and it will be okay. For zero sequence, always infinite, do not try to ground central point of a synchronous machine. It will die and die shortly because of rotor overheat. I left you to think why. What's next? Kind of wind parks and photovoltaics. This, let's say, PV array, they are connected to net with the help of inverter. Only inverter parameters are relevant. And for inverters, in case of direct sequence, inverters operate a bit interesting. If current is above threshold, something nominal or 1.1, it's nominal. It acts as an AMF. It keeps voltage. If current, output current of inverter, exceeds 1.1, 1.2 nominal as programmed, maybe even 1 nominal, inverter will go into current limiting mode. Inverter itself, some had so-called crowbar network, or current limiter, which start to cut off part of sign to reduce current. Anyway, the inverter will, if current exceeds this threshold, something approximately 1.1 in nominal, it will go into current limiting mode and will act as a current source of this threshold. For negative and zero sequence, nothing. Inverters do not allow true fall of negative sequence current or zero sequence current. Infinite. Next thing, important thing, transformers. Transformers. In general, you have some transformer. For this transformer, you need to get some digits. Digit number 1 for transient is so-called short circuit voltage. What's the idea? Transformer is power regulated source on the one side, and output is short-circuited. Voltage is raised until current here equals to nominal transformer rated current. This voltage, so short circuit experiment, voltage, when current equals to the transformer rated current, called short circuit voltage. I may use this symbol. Usually, manufacturers supply us with the data sheet where this voltage is nominated in percents. It's handy when you need to connect transformers in parallel, because you need this voltage to be equal on parallel transformer. This ensures that there will be no equalizing currents. It's interesting thing, this voltage in volts, in real name it values, very different for different kind of different transformers. But for here in Latvia, take any 110 kilowatt transformer, and they all will have 10.5% this voltage. And if you take this voltage relative to transformer nominal voltage, they all will be the same. It's a result of good design of transformers. Actually, most large transformer, you will see something between 10 and 11%. For some small, you may find 5. But in relative values, this voltage do not go far. Good. What this voltage gives to us? This voltage gives us, how to say, longitude resistance of transformer. It will be divided by 100 multiplied by rated voltage of our transformer in square divided by rated power in volt amperes of our transformer. Transformer resistance. If you take deeper research, you can find one more parameter. It's a power of short circuit. Power consumed, active power consumed during this experiment. This gives you so-called copper losses, losses in copper. Equivalent resistance of transformer can be found as this short circuit power multiplied by square of rated voltage divided by square of transformer rated power. And transformer reactance can be defined as a square root transformer minus R transformer squared from a full resistance. This is general thing about transformer. Now deeper. We have three phases. Version 1. Delta star fold. Direct negative sequence Z transformer or approximately for active resistance plays any significant role only for small transformers above 2-5 kilovolt amperes for small transformers. For larger, you can you can assume what transformer full resistance is pure reactive. For the zero sequence, if there is a delta, there will be no flow of the zero sequence current. Meaning, what we have, what resistance? Infinity. Good. Next one. Delta, not grounded. Here can be grounded or not grounded, not important. Same thing. Nothing changes. No ground wire, no flow of zero sequence. Next version. Grounded. Delta, grounded, delta. Direct negative, the same. Here, not same. Zero sequence current inflows, inflow circuit, outflows, comes back, returns. In this case, we will have transformer resistance in sequence, in zero sequence circuit. For case delta grounded, zero sequence will be transformed forward. And our transformer in zero sequence circuit will appear with Z transformer reactance found from short circuit experiment or test. Next one. What if we have something like this? Grounded, delta, ungrounded, delta. It's a complex thing, it's a tricky moment. Here, should be careful. For direct and negative sequence, everything remains the same. Transformer resistance found from short circuit test. For zero sequence, here you should be aware. Here you can have problem. Version 1. Your transformer is actually a group of, or assembly of 3 single phase transformers. Such design appears when we deal with very small installations. So it was impossible to find compact 3-leg transformer. 3-leg transformer will be less expensive. So for economy, it's preferable to use 3-leg transformer. But not found. We found only single phase. We need a small group, I don't know, 1 kVA. And one of the possible things, network on the side is isolated neutral network. So we will have, let's say, 0, 0, 0 sequence current. Here triple 0 sequence current should be drawn. But since neutral on the left side is isolated, is 0, here is 0. What happens? 0 sequence flux can freely circulate in the cores, in the steel cores of this transformer. We have a closed steel loop. If we have a closed steel loop, we have a good magnetic conductivity, means high reactance. We will see what we will see. Here is our 0 sequence neutral. We will see only, can draw it. This one is handing magnetizing resistance of our transformer. These are negligible, only that mu. It's a high, thousands of ohms, high resistance. So, you can simply assure what in 0 sequence transformer reactance is infinite and there will be no 0 sequence current. Because here we have free closed magnetic loop. Good conditions for 0 sequence flux. Good conditions, high inductance. Oh, very high resistance in 0 sequence circuit. What can be next version? I didn't finish my idea. When such group can arrive and appear. Small one, when you don't have sufficient free-leg transformer. And very, very big one. At some point, your power plant or your substation has so monstrous power what your transformer, if you try to order free-leg normal three-phase transformer, this transformer will be so heavy, so huge, but it's impossible to get it in place. It's impossible to get it to a tunnel, it's impossible to get it by the railroad. It's so huge, so heavy, that it's impossible to transport it to place. At that moment, design team takes a deep breath and redesign three-phase transformer into a group of single-phase giants. It's when we speak on gigawatt power, not megawatt, but gigawatt. At that moment, traditional three-leg transformer, it's cheaper, but it became so large, with rated power of gigawatt, so large and heavy that it's impossible to transport. Okay, go to single phase, group of three single phase. So what I draw, usually it's for very large substations, where very high power and also very high voltages. $500, $750 megavolt and gigawatt ratings. Transformers are so huge that they are not fitting any transport. What can you do? Break apart. Okay, let's go forward. And in forward, another version. Let's assume you do this with three-leg transformer. Here is my three-leg transformer. I have grounded network and 0, 0 and 0. 0 sequence currents inflows into ground for triple U0. I will see what? 0 sequence flux, 0 sequence flux and 0 sequence flux. For direct sequence flux, we have something like this. And here, in the closing section, some of the flux will be 0, no problem. For 0 sequence flux, we see this. Some will be triple. And we have a situation where three cars want to cross one intersection simultaneously. No way. 0 sequence flux can close only through air. Only by air. In theory, such transformer should have 0 reactance. No, it's not true. Transformer has its vessel, has its some kind of shrouds, some support constructions around. Really, it will have a 0 sequence reactance approximately 4-5 X transformer. Not infinity, higher when it's longitude, but you will get something. Old time regulation evaluates such mode star, grounded star, up to 1.5 MVA. On the one hand, such transformers are cheapest one for distribution network. If you need to transformers, for example, 10 kV to 0.4, this will be the cheapest cheapest available on the market. But first problem, in case of load non-symmetry, you will have voltage symmetry distortion. Second problem, in case of non-symmetric load, zero sequence magnetic flux will close in transformer's vessel, and there is a weak point where closing this kind of roof attached to the main vessel. It has oil-tight sealing and set of bolts. So these bolts can overheat and burn out the sealing, causing oil leak and fire. One more problem, if you have high presence of the third harmonics, expect possible nighttime overvoltage. It's because of transformer core saturation. Oh, today in our local policy is to discontinue usage of such transformer. Our local policy is to decommission them. Zero sequence current can flow to transformer, but zero sequence magnetic flux will close in transformer vessel, causing it heating, possible overheating, possible fire. Yes. Another kind of transformer. Look at this one. 1, 2, 3. Look at this design. 1, 2, 3 legs. Transformer. One more. Okay. One more core. 1, 2, 3. Oops. One more. If you add one more leg to your transformer, you will create a path for, this will be triple zero sequence flux through this leg. You will create a path for zero sequence. Best, of course, design can have addition. This is 5-leg transformer. Also, so-called armor design transformer. They are manufactured. Special, one of the super design has one more. is one solid. This O is one solid steel. So it kind of steel block here also. It's all closed. Each winding block sits in its own separate, how to say, sailing, but all this is like one, usually they are assembled vertical, one piece of steel. Such kind of transformers, screened or armored transformer, people speak what they are firstly designed for submarines to reduce, how to say, magnetic field of the submarine. But in reality, such transformers are used to power medical equipment, where high demands on voltage quality, intensive care units, operation units, cardiology, all kind. They have very high requirements on voltage quality. So such kind of transformers are used to power intensive therapies and so on. They are medical. One more design. Also closed design. Something. It's made of strange blocks of glued together, kind of semicircles. One core, two cores. And here, rooms for windings. Also closed magnetic system, such kind of transformers, strange, but they are very often used by, in elevators. Somewhere in the regulation hides what elevator is a kind of high risk machinery, and for high risk machinery, these transformers of such design recommended. In all such cases where we have additional legs, you may find transformer with design like this. 3 side legs and 1 central shaft. Delta, not linear arrangement of poles, but delta with the central leg. May appear as a large barrel. Inside, it's system with central leg. Also, the same thing. This leg creates a path for zero sequence. For all such kind of transformers, for zero sequence, we will have approximately infinite resistance. Very high zero sequence resistance. because zero sequence magnetic flux closes in additional leg, so on legs, and creates high reactive resistance, or low reactive conductivity. One more. Delta grounded star. Zero sequence current, zero sequence current, zero sequence current. Into ground flows triple zero sequence current. But what about delta side? On the delta side, for direct sequence, sum of the winding EMF is zero, and no current circulates. For zero sequence current, sum of the winding EMF will be triple, meaning what here will circulate zero sequence current of the primary side. Delta is a short circuit. Shortened circuit for zero sequence. Zero sequence current will circulate in delta connection. That means what in zero sequence current, magnetic analyze, we will need, so we have transformer leg, delta, zero sequence flux, and opposite zero sequence flux from this circulating current. Sum of zero sequence flux in leg will be zero. And in our schematic, transformer will appear as a transformer reactance connected to the common wire of zero sequence. Zero delta windings form a drain or sink for zero sequence. It's important. When we speak on earthfall protection, we should understand what zero sequence current will flow to the grounded neutral if there is a delta on possibility go forward. One special kind of transformer. When high asymmetry in load can be expected, so load is unevenly distributed by phase, to prevent voltage, neutral shift and voltage distortion, special kind of transformer can be used. Special transformer, zigzag or zigzag, for networks with asymmetry. Such transformer will have specific design of the winding. Okay. Will core primary winding is ordinary. On the primary side, everything is simple. Simple delta connection. A, B, C. But secondary side is something special. At secondary side, each winding is constructed of two parts. One occupies, how to say, own leg. Second one sits on the neighboring. So here is A1, A2. B1 and B2. And here first half of the phase C of the red phase, and here the second one. They are connected. Here A phase, here ground. Ground, B phase. They are connected in opposite. C phase, this one goes to ground. Here it is. Here is the schematics of winding for zigzag type of transformer. In case we have, let's say, zero sequence current and zero sequence flux, same zero sequence currents inflows here, and we will have opposite zero sequence flux. These two flux are eliminating one another. As a result, zero sequence resistance of such transformer is nearly zero. Approximately only active resisting of the wire, so it will be zero. Such transformer will have zero resistance in zero sequence current. Nearly zero. Special transformer. In case of direct sequence, you'll see something like A1 A2 equals minus B1 B1 it's B2 equals minus C1 and goes this way. C1 C2 equals minus A1. A phase voltage this one. It's a B phase voltage. Wait 1 second, wait 1 second, wait 1 second. No, that's not right. That's not right because C1 goes this way. This means what B2 should go this way, and this is B phase voltage. Sorry, this is B phase voltage, like this. So it's a special kind of transformer for network with high asymmetry of load, where phases are very different. In case of direct sequence, you will see something like this. But in case of zero sequence, this transformer presents nearly zero resistance, very small active resistance. Yeah, special kind of transformer. What else? What else? Special case, you have something in planted in neutral wire. If you have, for example, delta star transformer and some Zn is here, equivalence for direct sequence, this changes nothing. For zero sequence, you will have Z transformer approximately X transformer triple neutral resistance. So planting a coil in transformers neutral can be used to reduce line to ground fault currents. Okay, what else? Yeah, synchronous compensators and synchronous motors as generators for short time. What else? What else? What else? About power lines. First, overhead lines. Overhead lines. Okay, one step back. Inductive reactance of the line is dependent on the distance between wires. The closer wires, the smaller will be reactance of the line. For overhead lines with sufficient distance between wires, for example, 110 kilovolts, 0 to active ohm per 1 kilometers, and 0.4 reactive ohm per 1 kilometer. It's a typical digit for direct and negative sequence. For zero sequence, effective resistance is approximately triple, so 3 times higher. For cable lines, it's not important, it's kind of air cable or ground weight cable. Reactive resistance is very small, something about 3 milliohms per kilometer. Active is determined by the material of conductor and cross-section of conductor. Zero sequence, really, exactly you need to calculate taking into account cable shelf. It's this. In reality, each line should have its data sheet, its passport. It should be in geo information system. It should be, should be, and you will find this data. If not, in this book, you can find a reference to electronic copy and just put it to Google Translator, there is exact manual how to calculate these numbers. How to calculate line resistance. This can be done. You just need know something. It's not so complicated, so you don't need some special knowledge, but put it in mind. In book, Carson's model is described, and usually data in the line reference are from Carson's model. It's a low frequency model. In case you need high frequency, get a good book or good software or hire something, because you will need much more complicated at first glance double tones extension, but in details you will need to calculate Hoffman by the Hoffman model. Hire someone or pay for good software. It's not so. It can be done with the help of let's say Scylla, but it's much more complex. Carson's model is easy, but Carson's model is for low frequency. And one more, Carson's model for lines going for Carson model may not work if you have a line on each face on its pole, and distance between face are larger than height. Be careful, they can be a problem. What else? Remember, in a lot of symmetrical components, influence between parallel line for direct and negative sequence in most cases can be neglected. But for zero sequence, this Modal effect is significant. Between parallel lines, magnetic coupling, you need only one, zero sequence magnetic coupling. This magnetic coupling, from all magnetic couplings, this coupling is significant. If you lucky, it will be calculated, already estimated for lines. Maybe in form of Modal inductance coefficient. But if you're not lucky, you need to calculate it. Same Carson's model will work for 50 or 60 Hz. But be careful. Do not rush. Do it all meticulously, because these Modal inductance are serious factor for starting from 110 kilovolts. The higher voltage, the more serious will be effect of line-to-line coupling. Do not ignore it. Okay, I'm out of time today. We'll continue with why I'm talking about all of this.